Hello and welcome to the GCSE Science Tutor. Today we're looking at Lesson 10, Group 1, the Alkali Metals. As the name of this lesson suggests, the alkali metals are found in Group 1, or Column 1 of the periodic table. Your task is to draw the electron configurations of the first three alkali metals, lithium, sodium and potassium. Pause the video now and I'll give you the answers in a few moments. Lithium has 3 electrons, as shown by the atomic number. The first 2 electrons go in the first shell and the final electron in the third shell. Sodium has 11, so 2 electrons followed by 8, followed by the last electron in the third shell. And potassium has 19 electrons, so 2, 8, 8 and 1 is its electron configuration. What do you notice they all have in common? That's right, they have 1 electron in their outer shell. And that's really important because it influences how they react. It means that they all behave in very similar ways when reacting with other chemicals. We say that they have similar chemical properties, and that is because they have the same number or 1 electron in their outer shell. This is a really common question, and I recommend you write this down. First, we are going to look at the alkali metals reactions with water. Copy the table below, watch the videos in the next few slides, and record your observations. Pause the video now to write down the table and the keywords on the right-hand side. We are first going to look at the reactions of lithium with water. You'll notice that lithium is in fact stored under oil, and this is to prevent it from reacting with the oxygen in the air. And in fact, if you take a closer look at lithium, you'll notice a black tarnish on the outside. That is in fact not lithium, it's lithium oxide, because the lithium has reacted with some of the oxygen. Lithium can be cut with a knife. It is a very soft metal, and you'll notice on the inside that the lithium is very shiny. With this, you can see that lithium is a typical metal and conducts electricity. A small piece of lithium is placed in a beaker of water, and you can note down your observations such as fizzing, floating, and eventually the lithium will disappear. Here we are collecting hydrogen gas in the test tube. Hydrogen gas can be detected through the squeaky pop test, which is where we take a lit splint or candle and it produces a squeaky pop and extinguishes the flame. Now let's look at sodium. Sodium, like lithium, is also kept under oil to reduce its reactions with oxygen in the air. Sodium is also very soft and can be cut by a knife, again revealing the shiny sodium on the inside. Sodium reacts much faster with the oxygen in the air and starts to tarnish very quickly to produce a black oxide layer, and again still conducts electricity as it's a metal. Placing a piece of sodium in the water, you will notice again that there's fizzing and floating of the metal on the water. This time sodium will melt into a ball until it eventually disappears. Now potassium. Potassium is very, very soft and will react even faster with the oxygen in the air. to lose its metallic luster to form a black oxide layer. It is so soft you can actually squash it with the side of a knife. It conducts electricity, as the others did, because it is a metal. And take a piece of potassium, add it to water, and you will produce a lilac flame, along with fizzing and floating. Finally, let's have a look at rubidium and cesium. We're going to start with rubidium, which produces sparks and a red flame. Here it is again, and is increasingly more violent than the previous three metals. Now let's look at the final metal of the group 1 metals, which is cesium, which reacts so violently that it breaks the glass bowl. Here are some of the observations I made when the metals were reacting with the water. You can see as you move from lithium, sodium, potassium, rubidium and cesium, the reactions get more and more violent. And that is because the reactivity increases as you move down the group 1 elements. An exam tip is that you will often be asked to compare the reactions of the metals. So for example, you could say that sodium takes longer to disappear and moves more slowly. A common question is to ask about your observations with potassium, and it's important to say that it is a lilac flame rather than a purple flame, as they are very specific. With the observations made in those experiments, sometimes we are asked to give explanations or reasons for those observations. Have a go at explaining the observations made on the left. You could either try and come up with the explanations yourself or use the suggestions on the right-hand side, and I'll go through the answers in a moment. Number 1, the lithium and sodium float on the water. And this was because they are less dense than water, which is rather unusual for a metal, as most metals will sink. The sodium melts into a ball because it has a low melting point. We saw fizzing because hydrogen gas is produced. The metals will disappear because they are used up in the reaction. If we were to add universal indicator, it would turn purple. And this is because we are producing a hydroxide solution at the end, which is alkaline, hence the name alkali metals. And finally, the metals are stored under oil, and this is to prevent them from reacting with the oxygen in the air. When lithium reacts with water, we can represent this as a word equation. So we can write lithium plus water gives lithium hydroxide plus hydrogen. Hydrogen was produced represented by the fizzing that we saw in our observations. Lithium hydroxide was the solution that was remaining in the beaker or in the trough, and it produces a purple alkaline colour with universal indicator. We could also add state symbols to this. Lithium was a solid piece of metal, so we can give it the state symbol of an S to mean solid. It is important to make this a lowercase letter, not a capital. Water is in a liquid state, so we can give it a lowercase l. Lithium hydroxide is a salt in solution, so we can give it the symbol AQ to mean aqueous, or dissolved in water. Hydrogen was a gas, so we give it the lowercase g to represent gas. All of the other metals react in exactly the same way. So for example, if we take sodium, sodium will also react with water to produce sodium hydroxide plus hydrogen. And the same goes with potassium, rubidium, cesium, and francium. With the reactions with oxygen, let's take lithium for example. When exposed to the air, lithium will react with the oxygen to produce lithium oxide, which was the black layer found on the outside. We could also put on state symbols for this. Lithium is in a solid state, so we get an S. Oxygen is a gas found in the air, and lithium oxide was the solid black layer found on the outside. Again, the other alkali metals will react in the same way with oxygen. So we can write potassium plus oxygen produces potassium oxide, and the state symbols would remain exactly the same again. So why does reactivity increase as you descend the group? This is a really popular question with examiners, and it is really important that you learn this answer. First, we need to look at the electronic structure. So lithium, which is less reactive than potassium, have different electronic structures. They both have one electron in the outer shell, which I'm going to draw on here, and give a negative charge. I have omitted all the other electrons on the other shells to avoid confusion. So both of these electrons on the outer shell of these atoms stay in orbit or are attracted to the positive nucleus in the center. There is an attractive force that exists between the outer electron and the positive nucleus, and we call that force an electrostatic attraction. It is important not to call it an electromagnetic force because that is wrong. It is an electrostatic force. Now both of these atoms, as they are unstable because they do not have a full outer shell. So when both of these atoms react, they aim to lose their outer electron to become stable. And the most reactive atom is the one that finds it the easiest to lose its outer electron. Now the explanation we can give is that because potassium is larger, the electrostatic attraction between the outer electron and the nucleus is going to be weaker, and therefore the outer electron is going to be more easily lost in a reaction. I would learn this explanation on the right-hand side. So as we go down the group, the atoms get larger. There is a weaker electrostatic attraction between the outer shell electron and the nucleus. It is important that we mention the word outer shell electron and not just electron. There is also more electron shielding. This means simply more electron shields in the way of the outer shell electron and the nucleus, which again weakens the force even more. The outer shell electron is therefore more easily lost and is therefore makes that atom more reactive. Now let's see what you know with a quiz. Question 1. Why do the alkali metals have similar chemical properties? They all have one electron in their outer shell, which means they all behave in very similar ways. Question 2. Why do alkali metals fizz when reacting with water? They produce hydrogen gas. Question 3. Why do alkali metals turn black when exposed to the air? That's right, they react with the oxygen to produce a metal oxide layer. Question 4. Describe the trend in reactivity down the group 1 metals. Remember, describe just means what is happening, You don't have to give reasons for your answer. As you descend the group, the metals get more reactive. And finally, question 5. State 2 safety precautions that should be used when reacting alkalite metals with water. We can use a safety screen, tongs to hold the metal, and stay a safe distance away from the reaction when it's being carried out. The next lesson in this unit is Lesson 11, Group 7, the halogens. Thank you for listening to the GCSE Science Tutor. Please remember to like and subscribe to get further updates on lessons and tutorials.